Okay, let's dive right into this explainer and demystify the incredible physics of how things move in our universe. Motion is absolutely everywhere, and today we're going to unpack the hidden rules that govern it. We'll be looking at kinematics, which is basically the study of how to describe motion without getting bogged down in what's actually causing it. We've got a great roadmap for this journey of progressive complexity today. Here is our agenda. 1. The basics of motion. 2. Velocity versus speed. 3. Understanding acceleration. 4. The kinematic equations. And 5. Physics in the real world. Let's get to it.
Section 1. The basics of motion.
Let's start right at the absolute fundamentals. Before we can calculate anything, we have to define what we're actually looking at. At its core, motion is simply a change in position over time. But to make studying this whole thing a lot easier, physicists use this brilliant little trick called the point-object approximation. Think about a car taking a really long road trip from one city to another. The car itself is so tiny compared to the hundreds of miles it travels that we can just treat it as a single moving dot. As long as the size of the object is negligible compared to the distance it moves, treating it as a point object makes the math incredibly clean and surprisingly accurate. And this matters because, well, motion is common to literally everything. Whether it's the blood flowing in your veins right now, you coasting down the street on a bicycle, or the Earth rotating and revolving around the sun, it all boils down to that simple definition: a change in position over time. Moving on to section 2, velocity versus speed. Now let's see how we actually measure how fast this motion is happening. We hear speed and velocity used interchangeably all the time, right? But in physics, they have very distinct meanings. The crucial part here is understanding the difference between average and instantaneous. Average velocity tells us how fast an object moved over a given time interval, but it doesn't tell us how fast it was moving at different moments during that trip. Imagine driving to the store. You speed up, you slow down for traffic, you stop at red lights. Your average velocity is just your total displacement divided by your total time. But your instantaneous speed, that's exactly what you see when you glance down at your car's speedometer for one specific millisecond. It's the exact magnitude of your velocity at that one specific instant. Now, what's really fascinating is how the math captures that exact instant. Take a look at this table. As our time interval, represented by delta t, shrinks down from 2 seconds to 1 to half a second down to 100th of a second, the average velocity actually hones in on a very specific number. In this case, 3.84 meters per second. And this brings us to a beautiful calculus concept called a limit. Now, don't let fancy calculus words scare you away. Zooming into a time interval until it becomes infinitesimally small is just a mathematical way of getting closer and closer until we're essentially freezing time. By taking the limit, as the time interval approaches 0, we capture the exact, precise moment you hit the brakes on your bike. And boom, that is your instantaneous velocity. All right, section 3, understanding acceleration. We've figured out how to measure speed and velocity, but in the real world, things rarely move at a perfectly constant speed. So how do we describe a change in velocity? Does it change with distance, or does it change with time? Galileo himself wrestled with this exact question when watching objects fall, trying to figure out the fundamental rule of speeding up. Through studying falling objects and balls rolling down ramps, Galileo brilliantly deduced that velocity changes over time. This realization gave us the formal definition of acceleration. It's simply the rate of change of velocity with respect to time. And this perfectly illustrates that acceleration is way more versatile than you might think. In everyday language, accelerating means speeding up, right? But in kinematics, acceleration just means any change in velocity. So it can be positive, meaning you're speeding up. It can be negative, meaning you're braking or slowing down. It can even be 0, which just means you're cruising along at a constant speed. Oh, and here is a fantastic visual trick. If you look at a velocity time graph, the area underneath that curve represents the object's total displacement. It's an amazing geometric shortcut to finding out exactly how far an object has traveled. Let's jump into section 4, the kinematic equations. This is where we build the ultimate toolkit for analyzing uniform motion. It's time to reveal the secret codes that let us predict the future of a moving object. For uniformly accelerated motion, meaning the acceleration stays constant, we have 3 core kinematic equations. First up, v equals v naught plus at. Second, x equals v naught t plus 1/2 at squared. And third, v squared equals v naught squared plus 2ax. I know, these formulas totally look like alphabet soup right now, but they are incredibly powerful tools. They beautifully link together 5 things: initial velocity, final velocity, time, distance, and acceleration. Honestly, you can think of these equations as a physics superpower. As long as the acceleration is constant, if you know just a few things about where a moving object starts and how it accelerates, you can literally predict exactly where it will end up. You can calculate the future position of a thrown ball or how fast a falling rock is going right before it hits the dirt. Finally, Section 5, Physics in the Real World. Theory is great, but let's pull all this abstract math out of the classroom and see how it actually operates in our everyday lives. Let's talk about free fall. Every single time you drop something, the Earth's gravity pulls it down. If we ignore air resistance, that object accelerates downward uniformly at -9.8 meters per second squared. That simple, constant number is the engine behind literally every falling object on our planet. And when you apply our kinematic equations to this constant acceleration, you get a fascinating result, known as Galileo's law of odd numbers. Because an object in free fall from rest is constantly accelerating at 9.8 meters per second squared, the distance it covers in each equal time interval explodes in a ratio of odd numbers, 1 to 3 to 5 to 7. It's this beautiful mathematical pattern hitting right there every time you drop a stone. Believe it or not, you can actually use this predictable downward acceleration to measure your own biology. There's this classic experiment to test human reaction time, which is basically the time it takes your brain to observe, think, and act. You just have a friend hold a ruler vertically through the gap between your open thumb and forefinger. Without warning, they drop it and you catch it as fast as you can. Once you catch it, you measure the distance the ruler fell through your fingers. Because we know the ruler started from rest, and we know gravity's constant acceleration, we can plug that distance right into our kinematic equations and solve for time. You can find out exactly how many fractions of a second your brain took to process that visual information and tell your hand to clamp down. It's so cool. But look, kinematics isn't just for neat parlor tricks with rulers. It has life or death implications on the road. Take the physics of braking distance. Using our equation v squared equals v naught squared plus 2ax, we can clearly see that stopping distance depends on your initial velocity and braking capacity. More importantly, it's proportional to the square of your initial velocity. This means that if you double your speed, your stopping distance doesn't just double, it increases by a factor of 4. This is exactly why school zones have such strict speed limits. Going just a little bit faster requires a massively larger distance to come to a complete stop. So I want to leave you with this thought for your next commute. If your car's speed doubles, your stopping distance quadruples. Knowing this kinematic reality, are you really leaving enough space on the road? Kinematics isn't just textbook math. It's the invisible rulebook keeping us safe every single day. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.